I had a Google Meet yesterday, and a couple of people came in, but afterwards I had a few questions about wanting to go over things. So instead of me possibly having to spend another 45 minutes with a couple of meets, and I don't mind doing those types of things, but uh, becomes becomes a time where I can only explain things so many times during the day. So I'm going to go through some of the questions that were asked of me earlier today and put this together to see if I can answer some things. So in front of you right now, this is a solubility curve. Again, I know I did a video where I explained this, but I think after some of the questions I had today, I might be able to explain some of them a little bit better. Again, the idea here of what we've got is this is a picture of a situation. And so what we have, our situation is we have some water. That is indicated to us over here. And it's a specific amount of water. So if you see, it was actually over here. This would be for 100 grams of water. The reason being is this hopefully makes common sense to you, is that if you have more water, you should be able to dissolve more stuff in it. So for us to make some kind of a standard graph, we need to define how much water we have. So in this case, we've got 100 grams of water, which is also the same thing as 100 milliliters. And so this is a picture of what happens if we take potassium nitrate and dissolve it. It doesn't matter that you know what that is or you don't. What the curve shows us is that as we go from 0 degrees to 100, we're able to dissolve more and more and more KNO3. If we look down here at the very end, if this is 0 degrees, so this is effectively, that's freezing, then we could only put about, 20 grams in here. So we add 20 grams, we stir it up, and that's as much as that would be able to dissolve. If we tried to put another 10 grams into this, and no matter how much we stirred it or did anything, it would just go down to the bottom and it would not dissolve because it's too cold. There's just not enough energy to pull those things apart. Now, as we start heating it up, if we put a little flame in here and start my candle. You guys know I'm an awesome artist. If we start heating this up, now the temperature is going to start increasing. And as a lot of y'all wrote earlier this week, as the temperature starts going up, then we should be able to dissolve more. And so the stuff that would have been sitting at the bottom now is going to start dissolving. And so let's see if I can erase these little particles. They're not wanting to erase. That's fine, doesn't matter. But as we get up to, say, 50 degrees, now we're going to be able to dissolve up to about, 80 grams. So we could have added almost 4 times as much as we could here at the very beginning. So everywhere that this line is, this is showing us the maximum amount of KNO3 that we could put in this amount of water. If we put up to this line is the saturation line. Okay, again, saturation means that it is full. It cannot hold any more. So if I can get some of this off of the screen, we could say, therefore, that at -60 degrees, 100 grams of water, and with the 100 grams of water, the saturation point would be about 110 grams. So what if we only had 50 grams in here at this point? Well, we could put more. More would dissolve. So anything, if you graphed a dot anywhere below the line, we could describe that as being unsaturated. Because if we put a dot right here, if it's at 60 degrees and we only put 50 grams in there, well, we could add more. And by definition, if we could add more, that means that we have an unsaturated solution. Once we get to hit the line, no more is going to dissolve. And then at the line, it's going to become a saturated solution. There was a third term that was given to us called supersaturated, because super means above and beyond. It means more than. And that would be if we actually had, somehow, if we had 60 degrees of water and we somehow still had 150 grams dissolved in there. Now you may ask yourself, how the heck does that happen? Well, normally it doesn't, and this is something that doesn't happen very often in normal situations. What would have to happen is we would actually have to heat the water up to at least this point to get that 150 grams to be able to dissolve, because that's the saturation point. And then what we would need to do is actually to cool the water back off. And if this is done under very specific circumstances, the amount of KNO3 that we dissolved actually would stay dissolved. And so as it cools, still it should only be able to hold this amount, but it would still have 150 grams in it. So if for some reason we were able to have anywhere above the line, if we had a dot, so if somehow we had at 40 degrees, if we had 200 grams dissolved, that's way more than should be able to dissolve. So if we look at it above the line, that's what's going to be supersaturated. Okay, so if we go through and look at this again, if we dissolve something on the line, that's the saturation point. If we dissolve something where it's beneath the line, then it's unsaturated, because we should be able to dissolve more. And if somehow we've got a dot above the top up here, then that is going to be supersaturated. This is another graph that you had on the assignment today, and it's just got 4 different substances. Again, it's the same type of graph. We look over here and it tells us what do we have. We've got 100 grams of water. So we've got a certain amount of liquid that we're talking about. And we've got 4 different substances that we're putting into it. 3 of the lines go in the upward direction, 1 of them goes down. So let's look at A, B, and C, because A, B, and C, we have a relationship is that as the temperature goes up, then the amount that dissolves is going to go up. First of all, so that's an indication that it's very likely going to be a solid, because that's typically what solids do. If a solid is soluble in a liquid, usually it's going to be more soluble the hotter the liquid is. Now, they don't all happen at the same rate, however. Well, that's just one of the properties of substances. And so you may have a question on the assignment that says which has the greatest rate of change or which has the lowest rate of change. Well, that kind of goes back to your math questions of slope, because slope always tells us about a rate of change. So if we look at the slopes of these, line B would have the smallest slope, therefore it would have the least rate of change. And that kind of makes sense. That's saying whatever the substance is, that when it's cold or when it's hot, there's not a whole lot of change in how much we could dissolve. Whereas if we look at substance C, when it's cold, very little will dissolve. When it's hot, a lot of it will dissolve. So there's a great rate of change in that one. So again, if you're wanting to answer questions or understand what about the rate of change, then that simply has to do with the slope. Substance D, on the other hand, goes down. It has a negative slope. So as the temperature goes up, then the amount that's able to dissolve goes down. This is typical of, not of liquid. This is typical of when we have a gas dissolved inside the liquid. Gases don't like to stay inside of a liquid. Some of y'all put that answer with our video the other day. One of the things that will help a gas to stay in a liquid, one is if we keep it under pressure. It's like when you keep the lid or keep the cap on a bottle of soda like a Coke, that keeps the carbonation or the carbon dioxide inside. One of the other things that will keep the carbon dioxide in as well is we want to keep it as cold as possible. And so if it's cold, the gas particles can't really get up to the surface as much, they don't move around as much, and they're going to be much more likely to stay dissolved. But the big picture here is when we see these lines, if they're going up, that's usually going to be a solid. And if they're going down, that's typically going to be a gas. This is another graph that you had on the assignment. There was a couple of questions that went along with it. Before we look at those questions, though, we could look at these graphs and get some ideas. There's 5 things on here. We could infer that all of these are solids because they all go in the upward direction. They don't all have the same rate of change. The one that probably has the lowest rate of change is the sodium chloride, which is your table salt, because the line is the flattest. Again, it doesn't matter if it's freezing, it doesn't matter if it's boiling. There's very little change in how much of it we would end up dissolving. Again, another thing to look at over here is what are we talking about? This is saying, again, we've got 100 cubic centimeters, which is the same thing as a milliliter. So again, we're talking about how much could we dissolve in a certain amount of liquid as we change the temperature. So you had a couple of questions, and one of them was just asking what vocabulary word would we use to describe if we had something on there. So I'm not going to use the same one, but let's say we had at 30 degrees, if we dissolved 70 grams. And let's say we're talking about the sodium nitrate. So what I'm looking at here is this, again, like I talked about in the first graph, the solid line is indicating where is it saturated. In other words, this is the full line. If anything up to this, we can continue adding more and more and more. Because remember, as we go up the graph, we're talking about adding the solid into it. If we put a dot here on our graph, so if we say at 30 degrees, we add 70 grams, then it's below the dot. And so at this point, we would describe this as an unsaturated solution. If we added 30 more grams to it, then 70 plus 30 would get us up here. That will put us above the line. And if we're above the line, then that would be supersaturated. But then what if I heated it another 15 degrees? If I heated it another 15 degrees, that would change my temperature from 30 to 45, and then that would put me over here. Again, I'm back under the line at this point. And if my dot is graphed under the line, then it's going to be back to being an unsaturated solution. So again, as you decide whether or not something's saturated, whether or not something's unsaturated, or whether or not something's supersaturated, it's simply an idea of graphing the dot somewhere on the graph and then answering it in terms of where is it in relation to the line. So again, like with the potassium iodide, if I graph any dot below it, that's an unsaturated. If I graphed any dot above it, that would be supersaturated. Some good writing there. And if we graphed anything on the dot, on the line exactly, that would be saturated. One other question that's on there too that threw curveball with some people, and this is probably the last thing I can go over before I run out of time on this, is what if I had 300 milliliters or 300 grams of water? Well, hopefully that makes sense. If this graph is telling me that I've got 100, but what if I went to 300? Well, if I could dissolve, let's say if I can only dissolve 50 grams in this, how much could I dissolve in this? Well, it just becomes a ratio. If I could do 50 and 100, if I use 3 times as much water, I should be able to dissolve 3 times as much stuff in it, which would take me to, should be able to dissolve 150. Okay. Real quickly, same thing, if I had 100 grams of water and I increased it to 400 grams of water, then whatever I dissolved in here, I should be able to dissolve 4 times that amount in there. Same thing that you'd be doing in the kitchen. If you got more liquid, you should be able to dissolve more into it.